Okay, so in this video we're going to talk about definitions and theorems. Alright, so in going off with average value, okay, and somebody in here, or everybody at home said, hey Rock, which one of these looks like the average rate of change of something given that your first x value is -3 and your second x value is 5? Which one of these? I mean, and don't focus on the fact that this is cosine x. Don't think too hard about this. First of all, what would your denominator be? It should be the subtraction, right? So 8. So I'm going to get rid of these 3 right here. All right, which one do you think it is? A or E? Which one is like a function of 5 minus a function of -3? E. All right, now I'm not going to go too much more into this problem, but average value is not the same thing as average rate of change. Average value actually has more to do with integrating. All right, it has to do with the 1 over b minus a, integrating a to b. In this case, they say of cosine x. All right, on this problem, though, we really didn't have to go that far. Because of the way the answer choices were, this was easier. Now, the reason I bring this up is because you're going to have average rate of change and average value in number 3. So that's average value. Right here, I'm going to write average rate of change. That would just be like the slope of the secant line. F of b minus f of a over b minus a. Okay? A rock has to do with derivatives, and this average value has to do with integrating, although they're not completely separate things. Okay? All right, so what we are going to do now is work a different problem. Does everybody have that? Okay. So I'm not going to work 3. I'm going to let you work out 3 and work out the kinks of trying to figure out the difference between the whole average value and average rate of change and all that. Okay, but I do want you to look at number 4. Okay. So number 4, we have a function that is continuous, and again we have a closed interval. So I'm using x1 and x2 here, and I'm just really doing this. We could use a and b and all that kind of stuff, but I want to really point out that these are x values. This is an x value of -3 and an x value of 6. And then they go ahead and give us then our y values. All right, and I'm going to go ahead and graph this just so we get a really good idea of what's happening. So -3, -1, that's down here, and then 6, 3 is up here. Okay, so I have some function that at least goes from this point to this point. It is continuous. Does continuous mean it has to be a diagonal line? No. Could it have curves in it? Could the curves go way up and way down, and would that still be continuous?
Yes.
Yeah, and that's kind of the most crazy scenario. So if I'm going to work through a problem and I want to know something about it being must be true or guarantees, I don't want to draw the easy scenario because I might be tricked into thinking something's my answer when it's not. I'm going to draw a weird scenario. Okay? Continuous, though, does mean we could not have holes or vertical asymptotes. That's for sure not going to be on there. All right, so looking at choice A. Well, actually, let me back up just a second. Intermediate value theorem. You probably don't remember exactly what this theorem states, but what does the word intermediate mean? In the middle, somewhere. Maybe not like the exact middle, like midpoint, but somewhere in between. All right, so let me show you. So you have your x values at the endpoints. And this is saying that all the x values we know are going to be taken up. In other words, the domain is not going to skip anything. There's no holes or no vertical asymptotes. And at least from here to here, all of the y values will be taken care of at least once. All right? Now, I drew this in such a way that there are several y values of, say, y equals 1, y equals 2, y equals 3. And you could even have y values that are bigger, but you're going to for sure have y values in between. That's intermediate value theorem in a nutshell, okay? So I'm not going to get too technical with you on this, but that's what you need to know. That's what we're talking about here. So does that theorem say that f of 0 would have to be 0? And it didn't even matter what theorem we had. F of 0 does not have to be 0 unless they tell you, okay? That's not my answer. Okay, B says f prime of C equals 4/9, for at least one C between -3 and 6. So it's saying for these x values, your derivative or your slope has to be 4/9. Now, do you think that that could be true?
I'm sure it could be.
It could be true.
You're sure it could be true. Are you sure it must be true?
No.
I'm going to tell you that it is true, but it has nothing to do with intermediate value theorem. Okay, one of you said this earlier. What, and let me just draw this. And I'm going to put in a word here, average rate of change. What's another word we have for average? Mean. And so this is actually the mean value theorem. This is related to the mean value theorem, okay? So what they did is they found the slope between these 2 points, okay? And that is 4/9. So if the average rate of change, AROC, okay, what mean value, and I'm saying this because you're going to need mean value theorem on another problem. So let me just go ahead and X this off so we know. This is not our answer because that has nothing to do with intermediate value theorem. But what mean value theorem is saying is that the average rate of change must equal the actual instantaneous rate of change at C, okay, or the f prime of C. In other words, you're changing and it's like going blah, 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 but your average rate of change, whatever that value is, you're going to have at least one derivative somewhere that equals that same ratio. Does that make sense? At instantaneous rate of change, that's your derivative. Average rate of change, that's the slope just from point to point. Those 2 things do have to be true for at least one value, but again, not intermediate value here. Okay, so let's look at C. -1 is less than or equal to f of x, and let's just put a y value on top of f of x. Less than or equal to 3. Is that true? Is -1 less than or equal to y, which is less than or equal to 3? Okay, so so it is true some of the time, but not for all the x's, right? And this is why drawing the graph really wacky helps you out. Because if you had just drawn a really simple graph, you might think, well, yeah, your y's have to stay right there. But you could go up, you could go down. So, you know, even if you were doing this problem and you put a question mark here, there's going to be one in a second you're going to notice for sure, okay? But it is not the answer either. All right, so then the answer has to be D or E. Does, and again, in place of f of C, I want you to write y. And what could we put in place of C? X. So does y have to equal 1 for at least one x between -3 and 6? Yeah. In order for these 2 to connect, no matter how wacky or simple this graph is, this does have to be true. Okay? What is the problem with E?
It's -1 and 3.
Yeah, they're trying to switch it up on you. These are your y bounds. That's the only thing that makes this wrong. That's the only thing that makes E wrong. Okay, so average rate of change, average value, intermediate value theorem, mean value theorem. Okay, so all those things. Turn to the page, and I want to look at number 9. And your number 9 has a little double asterisk on it, so I want to do this. You do this as well. So what does that mean, by the way? It means we can use our calculator. All right, so I want to talk about, you know, if we can't think about what this problem is without the calculator, actually using the calculator won't help us. So let's see what we can deduce without it. So we have a piecewise function, okay? And I know that the top function is the function, except for one value, all right? 0. And that is because when you plug 0 in for x, you get sine of 0 over 0, which is 0 over 0. So what's happening at x equals 0 in this top function? There's a hole. So what the piecewise function does instead is, you know, because we want this f of x to be continuous, so we got to fill up that hole, right? So down here, there's some value, k, and we're going to have to find out what it is. And so, in other words, and this is where your calculator comes into play. You could graph this. So if you have your calculator, go ahead and plug sin x divided by x into y1. I'm not going to pull my calculator out up here because we really don't need it that much. Alright. But if we were to graph sine x over x, it would kind of look like a trig curve, but it looks really weird on the ends, and this is what's happening. So, at x equals 0, okay, we know that there's a hole. There's a hole right there. Now, your calculator doesn't show big circles for holes. It just skips that 1 pixel, which you may or may not even be able to see. All right, so this is where you still had to be able to do some of this without. So my question is, well, what is the y value at that hole? That's what my k should be. It should be whatever that y value is. Remember, this is the point down here, and I want this point to go in and fill up that hole. All right, now you could look at this on your calculator. How could you do this on your calculator?
Table.
You could go to the table. What could you do on the graph? We don't do this very much in here. But how could you get your cursor really close to this? Trace or just move the arrows. All right. I want to show you something you already know how to do, which is if I can't plug 0 in for x, I want to know what happens when x is really, really, really close to 0. And when I say really, really close, what am I talking about? The limit. Now, I bring this up really just to review limits, because if you use a calculator, you already know that this is a 1. Okay, so I'm going to go ahead and tell you, that's the answer, 1. All right, but I want to bring this up one more time. Okay, on the A/B test, you will not ask to do a limit like this without a calculator, but it actually is really easy to do using our new L'Hopital's rule. Okay, so when you plug 0 in and you get 0 over 0, and there's no way to like factor or something like that, you can use the calculator and use the table, or you can use L'Hopital's rule, which means you just take the derivative of the top, cosine x, take the derivative of the bottom, which would be 1, and you plug 0 in again. 0 cosine of 0, that's 1. So you actually know enough to do this without. All right? And the better you are without the calculator, I think the better you are with, because it uses just a tool and not something else. All right, turn to number 12. I'm really big on piecewise functions today, because these students scare students, but they're really not that bad. But looking at 12, I have a piecewise function. And so remember, our options for piecewise are you can have 2 separate functions coming together and meeting, which would be continuous. You could have it where they come together like this. You could have it where there's a hole like this, and there would be a jump discontinuity. You could have it where there's a cusp. Oops, I meant to put the point right there. You could have it where it's a line, and then where the point is, it's not a sharp turn. It's something like that. Okay, so there's a lot of different scenarios here. So what we're going to do now is kind of talk about continuity and discontinuity and differentiability with piecewise functions. Okay, so first, if I look at my options, first I need to just determine, is this thing continuous? Now you could graph this by hand. Do you want to graph this by hand?
No.
With natural log and e in it. Okay, me neither. All right, so what I'm going to do instead is I'm just going to find f of e. In other words, I'm kind of what I'm doing is finding the left-sided and right-sided limit. And I'm going to do that by just plugging e in. Now, as long as I don't get 0 over 0, this is how I should be able to do a limit. So the right-sided limit for x greater than e, that should be the same as natural log of e, which is equal to 1. So in other words, when x equals e, the right side of this graph, the y value, is 1. In order for this to be continuous, that same thing has to happen on the second part. Okay, so we have 1 over e x, and remember x here is e,
1.
and that's also 1. So this means that the 2 pieces are connecting. All right, so I do have continuity. Yes, that's because these two numbers are the exact same. Their y value is the same. One of them has a hole, one of them covers up the hole. So which answer choices can I get rid of?
D.
I can get rid of D. I can also get rid of C because it's not continuous. What about E? F of x is undefined at x equals E.
Oh, wait, sorry, I was thinking wrong. Because it can have a cusp and it's still continuous.
You can have a cusp and it's still continuous. That's going to get into the whole differentiable thing, which I will do in here in just a moment. But what I'm asking now is f of x undefined at x equals E? Yeah, we found f of E. If you can find f of E, then it's not undefined. Undefined would be when we plug in E and we get like 5 over 0, or square root of -10, or something that we cannot compute. That would be undefined. All right, so we got to narrow down to A and B. All we need to do now is do differentiability. Okay, so to do differentiability, what this is talking about is the derivative, all right, which would mean slope. Okay, so let's actually find the derivative. And let's just do the derivative of each piece. So what would the derivative of the top piece be? Let's see. 1 over x. What's the derivative of the bottom piece? 1 over e. Okay, I'm just doing derivatives. All right. So now again, I'm going to plug in e. And what we're looking for is that we already know they connect. But do they connect where their slopes are the exact same at that point of connection? That's what I'm really testing here. So if I plug e in, that 1 over x becomes 1 over e. The 1 over e stays 1 over e. Yes, they are. This is differentiable. This means that you have two totally different curves coming together, and at their point of connection, the slopes are exactly the same. This is not a cusp. Okay? If these two things are different, that would be a cusp, and that would be not differentiable. All right, so then our answer is A. And we can say f is continuous and differentiable everywhere because we tested at the point of connection, but natural log x is differentiable. I already took the derivative of it. 1 over ex, I took the derivative of it, so we can say for sure that these are differentiable everywhere. So that's kind of how you go about those problems. All right, turn now. 17 is the mean value theorem. I'm going to let you kind of do this one on your own. All right, but I do want you to go ahead and write what mean value theorem is. It's when average rate of change is equal to instantaneous rate of change. And remember, instantaneous rate of change is f prime of x or f prime of c, like some specific value. It's not saying that the derivative is always the average. It just means that whatever you get for your average rate of change, there's at least one value where the derivative is that same slope, okay? I want you to work this one out because it has tons of trig in it. So I want you to at least try it before I work it out. All right, let's look at number 19. All right, I'm going to work 19, and then 20 and 21 are pretty similar to this. And I know your page looks a little bit different than this, but this problem looks the same. All right, so on 19, I see limit as h approaches 0. This to me sounds like something very specific, which is the limit definition of the derivative. So the limit as h approaches 0 of f of x plus h minus f of x all over h. This is the way you do a derivative when you don't know how to do the derivative, okay? Which I made you guys do for like one day before I taught you the shortcuts, all right? The AP test, though, is tricky about how they ask these questions. So what they're going to do is try to tell you, hey, this is a limit problem, and it's a limit problem you can't get by just doing limits. So in other words, let's try. If we were to plug 0 in for h, what would we get?
You get 0 over 0.
You would get 0 over 0, because those two h's would go through 0, or that made it look like I was canceling, which I'm not, which is one of those things that makes me cry. All right, so you would get 0 over 0. This tells us that the limit does exist, okay? Not that it doesn't exist. So some people might want to just circle E and D done, and they're wrong. So what else do we have?
Negative x. Take the derivative of that.
So we could use the L'Hopital's rule. Do you know how to take the derivative of absolute value of x plus h?
Well, no, I meant take the derivative of the negative x. Make a shortcut.
Okay, right. We are going to do that. I guess what I'm saying is you cannot do this using traditional limits. You can't use L'Hopital's rule on this because you don't know how to take the derivative of absolute value of x plus h. We could take the derivative of just an absolute value by looking at the graph. And so that's what we're going to do here. So like what Brett was saying was, hey, if f of x is always this thing after the minus, all I really need to do is isolate f of x and find the derivative. And sometimes you're going to have to actually find the derivative at a number. Okay? In this case, we are. All right, now, if you can algebraically find the derivative, do that. We still, though, we do not know how to take the derivative of absolute value. There's no rule. Okay, what we're going to have to do instead is go back to basics. Here's the absolute value graph. Okay, I can't write what f prime of x is. I could write it as a piecewise function, but honestly, all I really want to know is what is the slope of this line when x equals 3? What's f prime of 3? 1. Slope of that line is 1. That's our answer. What if this had said at x equals 0? What would the answer be? Does not exist because there's a cusp. There's no derivative at 0. What if this had said x equals negative 2?
Negative 1.
The answer would be negative 1 because the slope over here on the left is negative. So that's what you're going to do. Like on your 19 and 20, you have to isolate the f of x. You are going, on the ones that you're going to be doing, you are going to be able to use algebra and calculus and all that to actually write the derivative. Then the very last thing is plug in a number if that's called for.
Did you know to draw?
This is a parent function you should know.
Oh.
If you don't know it, this is the time to learn it. So, yeah, it's just their standard V. If they give you something like this where you can't take the derivative algebraically, it'll be something really simple like this that you could graph. Really, absolute value is one of the only things that we just cannot take derivatives of. We have it in, some of our integral rules, but there's no absolute value rule. I'm not saying that doesn't exist. It's way more complicated than drawing it. All right?